The authors propose a residual neural network-based method, kNN-Res, for point set registration that preserves the topological structure of the target point set. This approach tackles the problem of aligning a deformed target set of d-dimensional points to a reference point set by applying a constrained transformation. The method is categorized as non-rigid and correspondence-free, allowing for flexibility in handling deformations. However, this also makes the problem ill-posed, requiring additional constraints. The alignment problem is formulated as finding a map that transforms data points sampled from an underlying distribution Q to distribution P, while preserving the topological structure of data sampled from Q. A Jacobian-based cost function and geometric-aware statistical distances are introduced to mitigate issues with existing approaches. The preservation of the k-nearest neighbor (kNN-Graph) of the target data is justified using the Jacobian cost. The problem is further formulated as finding a transformation phi that maximizes the statistical distance d between the transformed target set and the reference set, subject to preserving the kNN-Graph. A Jacobian orthogonality loss is introduced as a penalty term to preserve the kNN-Graph, which is a sufficient condition for preserving the topological structure of the data. The proposed method uses a scalable residual neural network (ResNet) architecture as the warping transformation and Hutchinson's estimator for fast computation of the Jacobian loss for high-dimensional point clouds. Geometry-aware statistical distances, such as Sinkhorn divergence, are used to address limitations of existing approaches. The method is demonstrated on several examples, including the Stanford Bunny, where the Jacobian penalty is shown to improve the learned transformation by preserving the topological structure of the data. Here is a combined summary of the 4 pages. Maximum mean discrepancy, MMD, is a measure of discrepancy between two probability distributions, alpha and beta, in a feature space X, using a kernel function k, x, y. However, MMD has limitations, such as being sensitive to the choice of kernel and suffering from the vanishing gradient problem. Optimal transport, OT, losses, on the other hand, do not have these issues but are computationally costly to solve. Entropic regularized OT, denoted as OTE, is an efficient approximation of OT that can be computed using the Sinkhorn algorithm. The Sinkhorn divergence, SE, combines the advantages of MMD and OT and is defined as the difference between OTE and the average of OTE for alpha and beta. The authors propose a novel approach to preserving the k-nearest neighbor (kNN-Graph) of data points under a transformation. They introduce a new distance metric, L1, theta, which is equivalent to the optimal transport distance between two measures, alpha and beta, over a reference and target distribution, respectively. This metric interpolates to the maximum mean discrepancy, MMD, as the cost function goes to infinity. The authors use a simple ResNet identity block as their transformation, where the output dimension is equal to the input dimension. The output is calculated as phi, y, theta, equals y plus delta, y, theta, where delta is a standard multi-layer perceptron, MLP, with leaky ReLU activation functions, and theta represents the trainable weights of the network. The authors show that the orthogonality of the Jacobian matrix evaluated at data points is a sufficient condition for preserving the kNN-Graph of the data. They introduce a Jacobian loss via finite difference, which can be computed using the PyTorch code provided in Algorithm 1. This loss measures the deviation of the Jacobian matrix from orthogonality at data points using the finite difference method. The authors demonstrate that the transformation preserves the kNN-Graph of the data points by showing that the squared Euclidean distance between 2 points, u and v, is equal to the squared distance between the transformed points, f, u, and f, v, under the orthogonality of the Jacobian matrix J. In the context of non-rigid point set registration, the authors introduce a novel approach to aligning high-dimensional data by leveraging the power of deep learning techniques. The proposed model, kNN-Res, utilizes a neural network to learn a non-rigid transformation that aligns 2 point sets while preserving neighborhood relationships. This is achieved through a loss function that combines the negative log likelihood of a Gaussian mixture model, GMM, with a mean squared error term between the kNN graphs of the input and output points. Additionally, an orthogonality loss is introduced to ensure the Jacobian of the transformation is orthogonal, which is crucial for preserving local geometry. To make the model scalable to high-dimensional data, the authors introduce a stochastic approximation of the Jacobian orthogonality loss using Hutchinson's estimator. This approximation significantly reduces computational complexity and allows for efficient training on large datasets. The training process involves mini-batching, blurring, and backpropagation, with several hyperparameters controlling the blurring, finite difference step size, and regularization strength. The authors provide PyTorch code for the Hutchinson approximation of Jacobian off-diagonal elements, which is essential for computing the Jacobian penalty during training. They also present experimental results on various datasets, including synthesized and real-world data. These experiments demonstrate the effectiveness of their kNN-Res model in aligning data under non-rigid deformations and preserving neighborhood relationships, outperforming several baseline models. Furthermore, the model is shown to be effective in high-dimensional data alignment, particularly in the presence of batch effects. Here is a combined summary of the 4 pages. Batch effects in high-dimensional single-cell data, particularly in CYTOF datasets, lead to non-biological variations during the measuring process, resulting in a distributional shift of samples and breaking intercomparability. To address this issue, the authors propose a novel method for aligning high-dimensional single-cell data across different batches using geometric constraints. This approach utilizes a vector field to align samples from the target and reference distributions, ensuring that the geometric relationships between cells in the high-dimensional space are preserved. The alignment process is demonstrated through 2 visual examples, a fish shape and a Chinese character, where the proposed method effectively aligns the deformed sets with the original ones. Quantitative evaluations using the Hamming loss metric show that the proposed method significantly outperforms the baseline alignment without geometric constraints. The method is further applied to a real-world dataset, illustrating the alignment of the first and second principal components of the reference and target samples. The authors also present a novel point set registration method, kNN-Res, which leverages a denoising autoencoder to remove zero values and standardize features. The kNN-Res model is trained with a custom loss function, incorporating a geometric constraint term to balance alignment and faithfulness to the original distribution. Experiments with different lambda values demonstrate that a small lambda favors alignment over faithfulness, while increasing lambda preserves the shape of the original data. The proposed method can effectively align high-dimensional data while preserving the topology of the original distribution. The authors visualize the alignment using the first 2 principal components and demonstrate that the learned transformation moves points in a coherent way. The method has potential applications in disease diagnosis and drug discovery, where maintaining the integrity of single-cell data is crucial. However, the authors acknowledge limitations, including the assumption of an orthogonal Jacobian, and propose future work to investigate the theoretical implications of relaxing this condition. The proposed point cloud registration framework, comprising a residual neural network, Jacobian penalty, and Sinkhorn divergence, addresses the limitations of existing methods. However, it has limitations, including the requirement for strict equality, which restricts its capabilities and slows convergence. Empirical evaluations are limited, and further experimentation is necessary to understand its limitations and applicability to real-world data. Future work includes incorporating local or partial matching using modified alignment losses, such as Gromov-Wasserstein distance, to improve robustness, particularly in cases with outliers or missing objects. Solving point set registration under topological constraints, like preserving the kNN-Graph, can be naturally extended to dimensionality reduction. The framework has been evaluated on synthetic and CYTOF datasets, demonstrating its flexibility and applicability in multiple domains. It has been compared to existing techniques, including those presented in references 14, which have been used for point cloud registration, 3D pose estimation, and image registration. A comprehensive literature review highlights various approaches, techniques, and methodologies for non-rigid point set registration, including Bayesian formulations, Gaussian process regression, and global-local topology preservation. The review covers topics such as coherent point drift, acceleration of non-rigid point set registration, and orthogonal Jacobian regularization for unsupervised disentanglement in image generation. The literature review also explores the use of stochastic estimators, Laplacian smoothing splines, and deep residual learning for image recognition, as well as kernel methods, optimal transport, and point matching algorithms. Recent advances in non-rigid point set registration, including coherent spatial mapping, global and local mixture distance-based methods, and feature-preserving simplification frameworks for 3D point clouds, are also discussed. Overall, the proposed framework offers a simple, scalable, and robust solution for point cloud registration, with potential applications in various fields. However, further research is necessary to address the limitations and explore the full potential of the approach. The referenced works on pages 21 and 22 provide a comprehensive overview of various techniques and methodologies in computer vision, pattern recognition, and machine learning. The citations discuss approaches for point cloud registration, graph matching, and non-rigid shape matching, highlighting the significance of developing robust and efficient algorithms. They also cover optimization and feature extraction techniques, including the atom optimization algorithm and denoising autoencoders. The CYTOF method, referenced in citation 50 and Appendix A, enables the simultaneous measurement of multiple proteins and transcripts in single cells, providing a powerful tool for single-cell analysis. The importance of normalization and standardization in single-cell analysis is also emphasized. The results presented on pages 23 and 24 demonstrate a method for aligning samples using a technique that incorporates geometric constraints. Principal component analysis, PCA, is used to represent high-dimensional data in a lower-dimensional space. The authors illustrate the effectiveness of introducing geometric constraints to the alignment procedure, showcasing significantly better preservation of spatial structures and improved representation in a topological context. Figures 8 and 9 visualize the results, with the blue dots representing the first and second principal components of the reference samples and the red dots representing the first and second principal components of the target samples. The introduction of geometric constraints, lambda equals 1, leads to a significant improvement in the alignment of the samples, enabling better representation of the data in a topological context. This alignment method has applications in manifold learning and image registration, and the inclusion of geometric constraints enables the preservation of spatial structure. The research paper presents a novel method for aligning point sets, which is crucial in various applications such as computer vision and robotics. This method utilizes a probabilistic framework, modeling the point sets as random variables, and computes the optimal transformation that maximizes the likelihood of the aligned point sets. An expectation maximization algorithm is employed to optimize the objective function, iteratively updating the transformation parameters and the point set assignments. The proposed method is robust and effective in aligning point sets, even in the presence of noise, outliers, and geometric constraints. It assumes a Gaussian distribution for the point sets, which may not always hold in practice. Future work involves exploring more robust distribution models and handling larger datasets. In addition to the alignment method, the paper also delves into the intricacies of immune system function, focusing on the role of CD28 and GZB in immune response. A detailed analysis of the marginals for these proteins is provided, highlighting their varying expression levels within different immune cell populations. This information is crucial for understanding how these proteins contribute to the immune response, particularly in the context of autoimmune diseases and cancer. The relationship between CD28 and GZB is explored further, discussing their synergistic effects on immune cell activation and regulation. The potential therapeutic implications of targeting these proteins in various immune-related disorders are also discussed, emphasizing the need for a balanced approach to avoid adverse side effects. The findings underscore the importance of understanding the complex interplay between CD28 and GZB to develop effective treatments for immune system disorders.